Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Pharmaceutical Organic Chemistry Paper 3. We are studying in Unit 4, Heterocycles Part 2. In the Lecture 6, we will be studying about Indole, Synthesis, Reactions and Applications. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. The topics that will be covered in this particular session include synthesis of indoles. We will be studying about the various synthetic methods of indole. First, we will be studying about Fischer-Indole synthesis, Bachelor synthesis, research synthesis, and the mechanism of research synthesis and other reactions also we will be studying. Then we will be studying about reactions of indole. Here we will be mainly focusing on electrophilic and nucleophilic reactions, conjugate addition reactions, Pichter-Spengler reactions, Vicarious nucleophilic substitution, ipso substitution of halogens, reactions with Michael acceptors. Let us now look at indole and its derivatives. Indole is a fusion of a benzene and a pyrrole ring. So this is the benzene ring and this is the pyrrole ring. So the fusion of these two actually is called as the indole. The indole is basically a prominent photoconstituent across various plant species. Tryptophan, which is an amino acid, serotonin and melatonin are animal hormones. Vincristine, vinblastine, vinorelbine are alkaloids are some of the very important indole derivatives. And in fact, if you look at the naming of indole, basically the name indole actually originated from India only. So from the India, the first they got the indigo color. The indigo color dyes were actually first used in India. So that is the name, this dye was given the name India, which is very similar to indigo. And from indigo, isotin was actually prepared and the isotin was converted to oxindole, and the oxindole was then reduced later on by Adolf von Baer to indole. So this is how the name indole actually originated from India, the name India. Let us look at the various reactions by which indoles can be prepared. So here is a schematic representation where the various ways how the indole nucleus can be formed are given here. This is ring 1, this is ring 2. So these two rings can be prepared separately. Either we prepare the ring 2 first and then make the ring 1, or we have the start with the ring 1 and then convert it to the ring 2. So both the ways we can actually make the indole derivatives, and some of the letters are given here, A, B, C, D, E, F, G, H, I and other things. So these are basically the breakage, which are all the bonds which can be broken or attached to form the indole derivative. So here if we wrote 1AB, that means basically in the ring 1, A and B are the bonds which are formed to make the indole derivative. In other words, this is the benzene unit, this is the nitrogen. So basically this is the aniline derivative which is having some groups here which can be converted or cyclized to form the indole derivative. So the starting material may be something substituted. This can be a carbonyl group which is present here. So this is amino carbonyl benzene derivative is the one which can be used as a starting material for the formation of indole. So the arrow as shown here basically is a retrosynthetic one, whereas the indole can be synthesized from this particular compound. That is what we mentioned here. When we talk about 1A, we have the benzene ring with the nitrogen, and we also have the extended arm which can simply undergo simple cyclization to form the ring. That is the 1A approach. And we have 1B approach where we have the substituted nitrogen here and this bond is formed these are all the various ways by which we can look at the 5-membered ring formation. And here we have some of the examples of the 6-membered ring formation. So we start with this is nothing but the pyrrole-like unit, and from this pyrrole-like unit we simply add 2 bonds to form the 6-membered ring. Or we can also start from this substituted pyrrole ring, and we can simply form this one bond, which can be further converted to indole unit, or maybe this top bond can be joined to form the indole. So these are all the various ways by which the 6-membered ring can be formed separately. So either way we can use, either we start with the 6-membered ring and build the 5-membered ring, or start from the 5-membered ring and then build the 6-membered ring. So either way we can actually make use of preparing this indole derivatives. We will look at some of the examples of these kind of reactions. The first one is the Fischer-Indole, the most famous Fischer-Indole synthesis. Here the indole is basically prepared from the action of acid or Lewis acid. Basically zinc chloride is a Lewis acid that is used here on the rearrangement of aryl hydrozones with the elimination of ammonia. So there are 2 nitrogens are there. So one of the nitrogen is lost as ammonia to form, because in the final indole we have only 1 nitrogen unit. So this can be formed from the starting material, which is the aryl hydrozone. The electron releasing group on the aromatic ring basically increases the reaction rates. That means if there is a substituent on this aromatic ring, that is if it is an electron releasing group, then this facilitates the cyclization very effectively. And the electron withdrawing group basically meta to the nitrogen gives equal amount of 4 and 6 disubstituted substituted indoles. So the cyclization can happen at 2 different places, either at this place or at this place. So that means it leads to 2 different type of products. Here let us look at the mechanism for this particular reaction. So the various steps involved are shown here. So the first thing basically the double bond is shifted from this carbon to this particular external carbon. So the external double bond as shown here is the first step which happens. This happens simply because of the addition of proton, because the addition of proton happens on this nitrogen, so which shifts the bond towards this carbon. And then basically cyclization like thing happens here. Basically the movements of electrons are shown here. Here the NH2 bond. Here again there is one more proton is added to this one, because here we have the NH, which is neutral. Proton addition leads to NH2 plus, and due to that there is a shift of electrons, in which case this carbon now forms a bond with the aromatic unit, and this particular bond which was existing before is actually converted to this particular nitrogen. So that means this internal double bond is moved to the nitrogen as externally shown here. So this leads to the nitrogen, which is having the lone pair, attacks this particular carbon, which is electrophilic, and now this can be lost as the ammonia unit as shown here. So this is the one we have been talking in the previous one, where the one of the nitrogen is lost as an ammonia molecule. So once this ammonia is lost, this carbon becomes a carbocation. To compensate that, the hydrogen is lost as a proton, and this bond shifts between these 2 carbons. Now the charge on this carbocation is neutralized, and we get a double bond here as shown here. So this is how the final cyclized product, that is the substituted indole, is formed. As we told earlier, there is a regiochemistry related to this formation of indole derivatives. Here we will look at one particular case where we get regio derivatives. So this hydrazine, phenyl hydrazine, reacts with the carbonyl compound, and the phenyl hydrazone is formed. And when the phenyl hydrazone is formed, this can undergo cyclization in the presence of acids. So we will see here there are 2 ways by which this particular reaction can actually take place. So here we have two possible tautomers which are possible in this particular case. That means the external CH2 bond, this is one type, another one here the bond is formed internally. So that way we have two types of tautomers which can actually form in this particular case, which leads to two different final products A and B. And because we are starting from an unsymmetrical ketone, so this is always possible to have one of the tautomer formed in large excess. So depending on the acid which we are using, if you use acetic acid, the product A is formed exclusively, that is at 100%. When we use polyphosphoric acid or methane sulfonic acid, the product B is formed relatively higher. So in the polyphosphoric acid we have 1:1 ratio of A and B, whereas when we use methane sulfonic acid we get maximum 78% of the product B formed in this particular reaction. So the regioselectivity can be controlled by the change of the corresponding acid which is used for the cyclization. There is another synthesis which is shown here. In this particular case, sulfuric acid is used as the reagent for the cyclization. The reaction actually occurs at very low temperature, that is at -5 degree. And here also we have another case where sulfuric acid is used as a reagent for the cyclization. Next one is the Bachelor synthesis. Here the alpha aryl aminoketones undergo cyclization to give the corresponding indole derivative. So here the polyphosphoric acid is the acid which is used for effecting this particular cyclization. The nitrogen is basically protected as its amide derivative, because this basically facilitates the effective cyclization. So the cyclization actually occurs as shown here. The proton from the acidic reagent adds to the carbonyl oxygen, so this becomes more electrophilic in nature, and aromatic ring is electron rich, so this pi bond now shifts towards the electrophilic carbon here, and which leads to basically the cyclization, and treatment of potassium hydroxide actually leads to the dehydration, and finally we end up with the substituted indole derivative as shown here. Next one is the research synthesis. So in this particular case, the nitro derivative, that is the nitrobenzene, nitrotoluene in this particular case, is reacted with oxalic diethyl oxalate, and this is the crucial one which is required, and this undergoes condensation reaction, and the nitro group is further reduced by tin and HCl to the amino group, and this undergoes cyclization because this nitrogen having the lone pair now is more nucleophilic, so this can attack this electrophilic carbonyl carbon, and the cyclization leads to this particular product, and hydrolysis of this ester and decarboxylation finally gives the indole. If you look at the reaction mechanism for this reaction, so that is explained here. The first step is basically the base abstraction of the methyl proton. So this is what is the crucial step we have to remember in this particular case. For this reaction to occur, we do need a methyl group here on this benzene ring, because this proton is the acidic proton, and this proton is abstracted by the methoxide anion. So the methoxide base, basically the methoxide base abstracts this proton, and a carbanion is generated on this particular carbon. Now this carbonyl, carbanion attacks the ester unit. The carbonyl carbon of this ester unit is being attacked. So this leads to this particular tetrahedral intermediate, and during the charge reversal step, the methoxide unit is lost, which gives the condensed product. So in the second step, what we say is basically the anionic attack of this electrophilic ester carbon happens, and the loss of methoxide from this particular tetrahedral intermediate leads to the our intermediate as shown here, and the nitro reduction is the next step, which is very crucial, because this nitro reduction actually creates the nucleophilic reagent for this particular cyclization. So once the reduction happens, we have a amino nitrogen. Here the amino nitrogen is having the lone pair of electrons, and that is the nucleophilic one for this particular cyclization. So this lone pair on nitrogen attacks the electrophilic carbon, leading to the cyclization and internal proton migration followed by loss of methanol and water molecules, as shown here in these particular steps, leads to this particular intermediate, and protonation of this carboxylate anion. That means basically we are doing the hydrolysis reaction. So the ester is basically converted to the acid, and this acid undergoes decarboxylation to give the corresponding indole. So the loss of CO2 is the crucial one, that is the CO2 loss, decarboxylation takes place, which leads to our final product. So this is the overall mechanism for this indole synthesis. So for this reaction to occur, the crucial part is we do need to have a methyl unit on the aromatic ring, and in the beginning we are not using the amino unit because that will actually leads to various side products in this particular reaction. So the required amino group which is required for the cyclization is generated after a couple of steps. So this is the synthetic beauty of some of these organic reactions. Now let us look at the reactions of indole. There is a lone pair of electrons on the nitrogen, that is the lone pair of electrons on the nitrogen is basically involved in the aromaticity. So this is not freely available, so that is the reason indole is a weak base. If you compare the previous case where we talked about pyridine, the nitrogen lone pair is basically perpendicular to the pi ring. The lone pair on the pyridine nitrogen was available to act as a base, whereas in the case of indoles, this particular lone pair is actually involved in the pi 6-membered ring pi aromatic nature, due to which this lone pair was not available for the on the nitrogen. So that is the reason this nitrogen is comparatively a weak base. And indole also exhibits some weak acidic properties because it forms salts with strong bases like potassium hydroxide. And when we talk about electrophilic attack, the electrophilic attack on indole basically happens on the pyrrole ring at position 3, which is the enamine site. So this carbon is the most electron rich carbon on this particular indole unit on the resonance forms. So that means the 3 position is the most favorable position for the electrophilic attack. This is followed by the nitrogen and then in the C2 positions. And of course, indole reacts much faster than benzene in the electrophilic reactions. The C2-C3 bond can also react like a alkene. So that means it can also undergo Diels-Alder reactions and other things. When the nitrogen is substituted, basically we can deprotonate the C2 carbon also. So these are some of the basic things we have to remember before we study more about the individual reactions. Some of the references are given here. If someone is interested, they can actually go through these papers where they have actually, these book chapters had extensively talked about the reactions of indole. Let us look at the electrophilic attack between 3 and 2 positions. So when the electrophile attacks, we had already seen that this carbon is the most electron rich carbon in this particular indole moiety. So the electrophile can effectively attack this 3 position. That leads to this particular intermediate, and this intermediate can actually exist in the resonance form as shown here. So this is one of the case where the positive charge can be easily delocalized. And if the electrophilic attack takes place on the second carbon, we only have one particular case where this is the only intermediate which is formed, which is also not resonance stabilized. So there are 2 favorable factors which prefer the electrophilic attack on 3 position. 1, this carbon is more electron rich, that is 1. 2, the attack of the electrophile on this carbon leads to an intermediate which can be resonance stabilized. So these are all the 2 reasons the 3 position attack of the electrophile is most favored in the case of indoles. Let us look at some of the examples. Nitration, when indole is treated for the nitration, we get the 3 substituted nitro derivative, and sulfonation leads to again the 3 substitution. Halogenation is quite interesting. When we do the halogenation with the bromine, we again get the 3 bromo derivative, and iodine DMF potassium hydroxide iodine treatment at room temperature again leads to 3 substituted derivatives. But when we look at the bromination, if we are using 2 equivalent of copper bromide and sodium hydroxide and silica, this specifically gives only the 3 substituted bromo derivative exclusively. That means at very high yield, 68%. But if the same reaction which is carried out in the absence of sodium hydroxide, we do get 2, that is dibromo derivative is formed as the major product. So this is one of the specific cases where if we want monobromo derivative, then the use of sodium hydroxide is very essential for this particular reaction. Whereas if we want the dibromo derivative, then TBAB can be used for this particular reaction. So the bromination can be effectively carried out to give different types of products. Then this is another important reaction for indole, because we will be looking at some of the important indole derivatives, because many alkaloids and other things are used as drugs and are also formed in nature. All of them have indole moiety. So how those kind of cyclization occurs is basically shown in this particular scheme. Basically, there is a nucleophilic substituent which is present on the 3 position after the electrophilic attack, and this can undergo basically a cyclization to give this particular cyclized, that is 3-ring fused derivative is formed. So basically many indole derivatives are multi-ring fused compounds. So this electrophilic substitution actually enables formation of these kind of rings. Then let us look at alkylations and benzylations. So this is very similar to the Friedel-Crafts reactions. So allyl bromide or benzyl bromide we can take and react with the indole in the presence of ammonium hydrogen carbonate, or basically even some Lewis acids. We can get the substitutions happening at 3 positions. So the 3 substitution actually occurs as the major product, that is the alkylation or benzylation takes place at this 3 position. Of course, at the 2 position also the reaction is happening, but the yield of this product is going to be very low. Then the next one is alkylation reaction by the conjugate addition reaction. So the N-substituted indoles or unsubstituted indole both undergo conjugate addition reactions with alpha beta unsaturated derivatives in the presence of Lewis acid. So many Lewis acids had been explored for this particular reaction, which leads to the 3 substitution, that is the conjugate addition takes place on the 3 position. Then next one is the managed reaction, which is the amino alkylation reaction. So here the alkylation by iminium ions basically here. So this iminium ion is formed by the reaction of formaldehyde and dimethylamine, which is the very simplest one to start with. This leads to the managed reaction, and finally we get the gramine, which is indole derivative. So here both the R groups are methyl groups, then this is the gramine derivative. So this is formed basically by the reaction of the formaldehyde and the dimethylamine with indoles. The next one is the Pichter-Spengler reaction. So this is again, as we have seen earlier, the indole derivative is very crucial derivative, and it gives the fused multi-cyclic systems or the spiro derivatives as shown here. So these are a couple of reactions which are very crucial and for the alkaloid and other product synthesis. And one such example is the Pichter-Spengler reaction. So here it is basically the intramolecular amino alkylation of tryptamine. So this is the tryptamine derivative, and this leads to our cyclized product. So if you are using the N-benzylidine tryptamine with Lewis acids, the initial attack basically occurs at the C3 position, and this forms the spiroindolinine intermediate as shown here. And because of the highly migratory tendency of the amino groups, basically the migration further takes place to 2 position, and then we end up with the beta carbolene as shown here. So this is one of the intermediate which can be trapped as shown here when we use this particular reagent. So we can actually stop the reaction at this particular intermediate and we can get this pyro derivative. If the reaction is allowed to proceed further, then we finally end up with this beta carbolene derivative as shown here. Like aromatic other heterocycles, the indole can also undergo Wills-Mayer-Hack formulation using POCl3 and DMF. So this leads to, as usual, the 3 position is the place where the substitution actually takes place. So the 3,4-methyl indoles are formed when indole is treated with POCl3 and DMF. We can also do searing acylation. So when this particular, see, the crucial thing in this particular reaction is the more when we have the acyl unit, which is the electron withdrawing group, the reaction occurs very effectively. That means if we have a 3,4-methyl derivative, the 3,4-methyl derivative actually facilitates this kind of searing acylation reaction. So when an acid chloride is treated with 3,4-methyl indoles in the presence of a large excess of AlCl3, that means this is not a Lewis acid catalyzed reaction. Basically, this is we are using the AlCl3, which is a Lewis acid in large quantities. So this leads to acylation on the aromatic ring. And after the acylation occurs on this one, palladium carbon reduction basically reduces this particular one. So this actually decarbonylation actually takes place when we do the reaction at a very high temperature. So the CHO group is lost to give the acyl substituted indole derivatives. Then if we have carboxylic acid, this molecule, the indoles can also undergo intramolecular acylation reaction. So this is basically the intramolecular Friedel-Crafts acylation reactions of 3-indole 3-aryl alkanoic acid. So here basically we have a carboxylic acid, and this carboxylic acid undergoes cyclization to give either 5-membered or the 6-membered derivatives based on what is the length of this CH2 unit. So this basically leads to 1-oxo-1,2,3,4 tetrahydrocarbazole derivative as shown here. Next, let us look at nucleophilic reaction. So indole is actually pi excessive heterocyclic ring system. So it is more likely to undergo electrophilic attack than the nucleophilic attack, which we already are familiar with. But it is also possible that nucleophilic substitution can happen on the indole derivative. When some electron withdrawing groups like nitro groups are present at various positions in the indole, then the nucleophilic substitution reaction is possible. The nitro group is present now on the aromatic ring, that is the benzene ring. So when there is an electron withdrawing group present, then this can actually undergo nucleophilic reaction. So treatment of this nitro derivative with the 3 equivalent of Grignard reagent and followed by K-amino oxidation leads to this particular nucleophilic substitutions on the aromatic ring. This is also another reaction when the carbocation can be added to this at the 3 position. So here we have a nitro derivative. Now the nitro derivatives on the pyrrole ring itself. Here again, when we treat with the 2 to 3 equivalent of Grignard reagent, the reaction actually occurs on 2 position as shown here. So these are some other examples of nucleophilic reactions. Then we have the Vicarious nucleophilic substitution. So the Vicarious nucleophilic substitution of hydrogen has successfully installed the alpha functionalized carbon side chains on the nitro indole. So when we have the nitro indole, so this particular group, the carbon can be carbon undergoes Vicarious nucleophilic substitution. So the chlorine is basically lost, and this CH2TS tosyl group is actually added to the aromatic ring. Ipso substitution is also possible with the help of halogen. So when there is a halogen, when it is treated with the silver nitrate, the halogen is replaced by the nitro group. So this ipso attack or the ipso substitution also takes place in the case of indole derivatives. Here is another example which is shown here. In this particular case, there is a formyl group at 3 position, and this halogen is now replaced by the pyrrole moiety. So that is what is this particular product is formed. The reaction of 2-chloro, 1-methoxymethyl indole, 3-carboxylaldehyde nucleophile is the pyrrole. When we use this, gives the nucleophilic ipso attack basically, and it also undergoes SN2 prime reaction at the C3 position. When an electron withdrawing group is present at 2 position, this basically activate this 3 position for the reaction for nucleophilic substitution. So dimethyl copper lithium reagent actually introduces a methyl group on this particular indole. Then the effect of electron withdrawing group on cyanation. So if there is an electron withdrawing group, especially the formyl group, then the cyanation actually takes place very effectively. Here if you look at, we get 98% of the cyanation which occurs on the 2 position, that is the nucleophilic substitution occurs here. If there is no formyl group, that is no electron withdrawing group on this particular unit, then the reaction actually occurs and we get only 2% of the product. So the electron withdrawing group plays a major role for the nucleophilic substitution reaction. That can be easily seen by this particular example. And here again there are some of the examples when formyl group is present, and we get around 70 to 90% here. Various nucleophiles can be introduced into the indole unit. When we use there is a formyl group which is present, which is an electron withdrawing group, which actually activates the indole ring for the nucleophilic substitution reaction. Plancher rearrangement. In this particular case, indole is treated with methyl iodide at a high temperature. So the monoalkylation takes place first, followed by the dialkylation, and this dialkylation actually happens on the same carbon, that is the C3 unit. Then this actually undergoes rearrangement to give the 2 and 3 substitution as shown here. So this is one another reaction of indoles. Then indole can also undergo reactions with Michael acceptor as shown here. The electron withdrawing group can be a nitro group, cyano group, or the acetyl group as shown here. Let us look at important drugs which have indole moiety. As I have mentioned earlier, indole is one of the very important class of heterocycle which is present in various drugs and alkaloids. So there are plenty of compounds which are known and the applications are shown here. Say for example, vincristine, vinblastine, all are anti-cancer compounds. We have roxindole which is used for schizophrenia, arbitol for used for the antiviral activities, pinodolol is used as an anti-hypertensive reagent. So yohimbine is used for sexual disorder. Bufotenidine is basically a toxin. Pravadolin is used as an analgesic. So pericin is an opioid agonist. So there are various drugs which are having the indole moiety. Let us look at a few of the examples here. Sumatriptan is one compound. This is used for the treatment of migraine, which is having the indole unit. Ondansetron is another compound which is used for the suppression of nausea and vomiting, which is caused by the cancer chemotherapy and radiotherapy. Lysergic acid diethylamide is also another drug which is used. Ellipticin is an anti-neoplastic agent. This is also having the indole moiety. Yohimbine is a drug for male impotency. This is having this particular indole moiety. And indomethacin is used for the treatment of rheumatoid arthritis. So there are various indole drugs which are used for the treatment of various diseases. In summary, let us recap what we have studied so far. We have studied about the various synthetic methods of indole. We studied about Fischer-Indole synthesis, Bachelor synthesis, research synthesis, and we also looked at the mechanism of research synthesis. We have then studied about various reactions of indoles, basically electrophilic and nucleophilic reactions, conjugate addition reactions, Pictet-Stringler reaction, Vicarious nucleophilic substitution, ipso substitutions of halogens, reactions with Michael acceptor. With that, we conclude this session on indoles. Thank you.